So last time we talked about an introduction to phase diagrams, and now this video is going to be about the lever rule. Now, I'm assuming most of the people who are watching this are trying to become, are majoring in engineering, so that's the reason why I'm following this path. So, anyway, last time I talked about a definition of a phase, and I specifically said that it's a description of the state of phases. I'm sorry, state of the system. So, the system could be, some kind of compound or series of compounds, but it could also, it could also be a substance and so on. So, and then I also talked about, but the thing about that definition is that I say that it's a description. So description is kind of vague. You're saying, well, what do you mean by that? Well, you'll see what I mean in this video because it specifically means something as far as understanding the terminology for material science. So and how you pretty much formalize everything. So, but the very simplistic scientific definition would be that it's just a region of states. So you might have a region of solid phase, and so that or a solid state, and so that would be the solid phase. And so that's just what a phase is. It's that simple. But when it comes to what I'm going to talk about, you'll see that it is in fact a description. So anyway, when we introduce the lever rule, we actually give a very hypothetical situation. So suppose we have A, which is metal, and let me write that bigger. Try to write it bigger. We have A, which is metal number one, number one, and then B, which is metal number two. And suppose these two metals were to form an alloy. So the alloy would just be AB. Now, the alloy AB, though, in this hypothetical situation, only has two states. That is not very common, and actually not very realistic. Usually it's more than two. Much, you'll see that much later. I mean, you'll see that a little bit later, but it's far greater than two. So in that case, we can also make a phase diagram to show of a compositional phase diagram. Let me make this straight. Whatever. Okay, to show that now this is kind of going to look like a hysteresis type thing, just so that you can see. I mean, how else are we going to show you how the region might intersect, right? So we have alpha, which is solid, and then beta, which is liquid. So in between we have a combination of the two, right? All right. So at this point we have 100% A. At this point we'll have 100% B. So what that means is that at this point, if we have 100% A, we have 0% B. And if we have 100% B, and let me make that near the point where it's like right here, because it just makes more sense that way. So 100% B. And if we have 100% B, we have 0% A. So that kind of makes sense, right? Well, in some circumstances, you're going to see that it's not always going to be 100% on either end. And that might be because of the way the alloy is made. Mind you, each phase diagram is empirical. So that means that each phase diagram is based on some kind of data that you got from experiments and so on, from a laboratory. So you can't just theoretically put all these lines out here from equations and stuff. It makes no sense. Because I mean, you need a lot of you need a lot of empirical data in this to actually write the phase diagrams. So anyway, why is this useful, and why? And the question is, yeah, why is this useful? Why do we want to know about it, and why do we even need a hypothetical situation? Well, suppose now that we wanted to find, or that you were asked, because usually you're going to be asked these questions, and well, before I go into that, usually and by the way, this is temperature, so you might have at this point like let's see, like 500 degrees Celsius and so on, and this will be 0 degrees Celsius, and so this will be useful in determining at certain temperatures and at certain points what the composition of B or A is, because for every B you're going to have the complement, which is just 100% minus that. So it's really because of the fact that this is a binary system. Now, if it was a ternary system, it's going to be a little bit more complicated. But if it's a binary system, it's very simple to understand, relatively. So, and that's all you're going to need to know for now and for a while. Ternary systems, I may not even cover that, but just keep in mind this is binary. So anyway, but binary alloys. So usually you're going to be asked, say, find the compositions of the phases. So when you're asked to find the composition of the phases, that's where a lot of people actually get lost. Because you're saying, well, alpha is a state, beta is also a state, correct? So are we finding the composition of the states? What do they mean by composition of phases? So it makes perfect sense to actually question in the first place, although, not very many people do. Instead, they just try to answer the question and they don't get it right. So the way that you handle this problem is you got to understand the definition of a phase. Remember, I said that it's a description of the states. So the fact that it's a description of states means that we're going to describe the composition of the alpha phase and the beta phase separately. You see what I mean? So that's the reason why I said description in the first place. So let me erase this part. I think you guys got this. So let's try to do this problem. So the way you solve this problem is you basically say, okay, in the alpha phase, we have a composition of A being equal to some number, right? And composition of B equal to some number. So how do you find these? Well, it's really simple because now, well, I'm sorry, I didn't give you really many givens, because basically it could be anywhere, right? So let's say we take a point here and we can call it gamma 1, right? So if we call this point gamma 1, then we'd say that gamma 1 is approximately at 500 degrees Celsius, which I don't know if you can see, but it can also be at approximately, let's see. Now, you can just, as far as eyeballing goes, I'm just going to eyeball it. Most of the time, if you're given a scale drawing, you could just kind of look at it. 50% A and 50% B, because it's going to lie exactly between A and B. It looks like it, right? If you have a scale drawing, you can use a ruler very well, and you can just draw a horizontal line here to figure out what the temperature is. Then at that point, the intersection, draw a vertical line to find the compositions. So in the alpha phase, and mind you, this is represented by gamma 1. So in the alpha phase, we have chi A, and I represent it by chi because we usually use chi to represent compositions in in chemistry, physics, whatever material science, and it's very convenient. You'll find that it's great. So this is 50%, and then this is 50%. And by the way, usually with this, we represent this as weight %. So, yeah, anyway. So, as you can see, these are the compositions in the alpha phase. And so this is what is described by the alpha phase. Now you see what I mean? Anyway, so now in the beta phase, we have chi A is equal to chi B is equal to 0%, correct? Because this point only exists in the alpha phase. It does not exist between, it doesn't exist in the beta phase. If it existed between, that's where the original point of this tutorial would lead us to. But it looks like I'm running out of time, so I'll probably talk about that in the next video. Anyway, yeah, this would be your answer for this problem, and that's just this point. Next video, I'll talk about the region between alpha and beta, which is much more complicated. It's a little bit more complicated, but it just requires actually requires the level rule. And I'll explain why. All right. Hopefully you enjoyed that.